the Kondo effect. So it is very well known many-body effect in Kondo system. So in this effect, even though the Coulomb repulsion prohibits the transport electrons through Kondo, the hybridization of the electron and the reservoir electron can lead to pronounced transport through the conductor. All these effects were studied in low frequencies, and some other groups even implemented the Mach-Zehner interferometer by using the electrons. So now, the next challenge for Mesoscopic system is to study the dynamics of the electrons in such kind of very small systems. So for example, here, so people want to study single electron. So usually the circuit, the current consists of many electrons. But since we are very interested in the quantum state of the electron and its use for the future quantum computing device, we want to pump out only one electron. So here, by applying the pulse, the people manage to pump out a single electron. Then, so that the people can measure the current as a function of time. So the question here to be answered is how well the electrons respond to the external perturbation. So does it react even enough fast, or whether we need some time to have some stable electron wave packets? Then people should think this as kind of RC circuit like this. So we can think of this system as a kind of circuit with resistance and capacitance. Actually, we have very good experience with these circuits. So, but in our usual experiment, this circuit, the resistance or capacitance are determined by classical electrodynamics. But in this case, we want to study the quantum mechanical correction to these basic circuits, basic elements of circuit. So mostly we want to know how fast this circuit can react to external perturbations. So it is very crucial to implement the quantum devices. So we need a quantum device which works in very high frequency. So by predicting some kind of reaction time of this circuit, we can know the limitation on our implementation of this kind of circuit. And more interestingly, by studying the finite frequency response of this system, we can extract more information about these systems, especially its many-body effect. So we are mostly concerned with the capacitance and resistance. So first look at the capacitance. Your capacitance are determined by the Coulomb interaction between electrons. And usually the capacitance, the usual capacitance, is determined by its geometry. So this capacitance is known as electrostatic geometrical capacitance. It is well-known capacitance. But there is more in Mesoscopic system. Actually, so the electric field can modify the band bottom of the band bottom by then we change the charges, the charge numbers in this lead. But we can also change the charge by changing the chemical potential. So there are two effects to induce charge at the gate, at this kind of plate. So we have this formula. So here C is the geometrical capacitance is defined with respect to the change in the band bottom. And C mu, so this is the electrochemical capacitance, which is quite accessible to it's measured in the experiment because it is measured with respect to change in chemical potential. It is much easier to tune the chemical potential rather than the bent bottom. Usually they are related to each other, but so the electrochemical capacitance, so it's given by some parallel sum of the electrostatic capacitance and a new one, which is called quantum capacitance, which is proportional to the density state of this system. In method, usually the density state is very high, very huge. It means that this number is almost zero. So in that case, the electrochemical capacitance is equal to the geometrical capacitance, so you don't have to worry about it. But in Mesoscopic system, the density state can be very small. Then we have very large contribution from the quantum capacitance. So one thing you should remember in my talk is that this quantum capacitance is proportional to the density state. So if there is a room for electron, then it can increase the capacitance because the system can accept electron. So we have the larger capacitance. But this formula is obtained in the mean field approach. So it does not care about some electron correlation in this system. So we will, in my study, I will present some another story for this quantum capacitance. And now I want to get how to calculate the resistance for this quantum dot system. So to do that, we need to calculate some admittance. So we are mostly interested in the linear response regime, so where the perturbation is very small. So every response is linear to the external perturbation. Then we can have some proportional constant between the response and the perturbation. So here G is the admittance of the inverse of the impedance. So now we apply some gate voltage to this quantum dot system, which can lead to some current between the quantum dot and the reservoir. So this is the current I. So actually, I now want to go to detailed derivation. So just I give you the result. So what we want to calculate is the admittance, which is given by the current divided by voltage. So or its inverse is the impedance. So we have two components here. This comes from the capacitance between the quantum dot and the gate, which is just this formula. This is the impedance from the capacitance, and the resistance, the information on resistance contained here. So we need to calculate this admittance by using using various methods. In 1990, the Whittaker really calculated admittance by using the scattering matrix. So here he assumed that the circuit is non-interacting. Then he effectively derived the effective scattering matrix. From that, he managed to get the admittance, and by inserting this formula to here, we can get the resistance by taking the real part of the impedance. So this is the formula for the resistance. And it can be in a simple form like this. So one thing is very interesting here is that if we have only one channel, so here the alpha is the channel index. So if we have only one channel and at zero temperature, so at zero temperature, this derivative of the Fermi distribution with respect to energy becomes the delta function. So this integration goes away, and we have same quantities in both the numerator and denominator, then we get a very unique some kind of constant, which is independent constant. So interesting is that usually the resistance should depend on the detail of the system. So maybe it should be related with how well these two parts are connected. If we block this connection, we will have infinite resistance. But the result is that we have kind of universal conductance and universal resistance. Then there must be some reason for obtaining the kind of universal values. I will explain later. But this resistance is the value at low frequency region. So in the limit where the frequency goes to 0. And actually at 0 frequency you should expect the DC resistance, which should depend on the detail of the system, the transmission. So here the low frequency is not really low frequency. So because at low frequency, so the time interval for each period is longer, and at some point the period is larger than the current time of the system. Then we should then some incurrent phenomena start to work, but this result comes from the assumption of coherent transport. So really at 0 frequency we should get to this DC value. So here so the frequency is not so low, but in my talk I will say this. I take this low frequency limit scale, assuming that the whole process are coherent. And next, and recently people introduced Coulomb interaction, then see how this value is changing. But they use the high-throughput approximation. This approximation does not really take into account the many-body effect. So they obtain the almost same result. So they have still they have the one half resistance here. I mean the one half means this 1/2 constant here. And if you have two channels, then you have two resistance in parallel. Then resistance is reduced by half. So then you should have 1/4. So their result so that the resistance is oscillate between two values depending on the density state at the quantum dot. So that it is the story before I studied this problem. So before beginning my work, before interested my work, I give you some idea why we have the universal constant. And before that, this is the experimental confirmation of this universal value. So really people measure the resistance and found that the resistance is almost same as this constant. So it's true. So it does not. This resistance seems to be quite independent of the system details or some rather high responses. And this universal value can be related to some Fermi liquid picture of the system. So the admittance, which admittance is a function between current and charge, can be related to the charge susceptibility through this simple formula. So since the charge susceptibility has this form, so the difference between two forms is that the admittance has the time derivative here. Then in frequency regions, we have the omega here. And by inserting this formula into here and taking the real part, we can have the formula for the resistance. Or in the limit where the frequency is 0, we have this formula. So if we have some nice relation between charge susceptibility at low frequency, especially in real part and image part, we will have some kind of constant for the resistance. And we have similar relation for spin susceptibility. It's known as the Koulomb relation. So for spin susceptibility, its image part has very simple. Image part has very simple relation with its real part. But this for the spin susceptibility. So a group may need to link to susceptibility by taking some the mapping our system into the Kondo model. So in Kondo model, all the charge fluctuation can be mapped into spin fluctuations. So in that case, our charge susceptibility is exactly equal to the spin susceptibility for this artificial spin. Then we have this value. So this is not just a coincidence to have this universal value. Its origin has a root in some Fermi-liquid nature of the system. But whatever we break the Fermi-liquid picture by considering the many-body case of the system. So our piston is like this. So we consider the strong many-body correlation and to see how this competence and resistance are changing. And also we want to see the high frequency response of the system. We will see very interesting features. And we also want to study how the spin interaction can affect the resistance. Actually, spin and charge looks separate property of the electron, but in many-body system they are relative. By introducing spin fluctuation or spin interaction, we can control the charge and vice versa. So we will see how it takes place in our system. So the system we want to study is this quantum system. So the quantum dot is coupled to a reservoir, and here we apply the AC voltage. The quantum dot can have many levels, but in the first part of our study, we have only one. We have a single level, and the second part we introduce two levels. And this quantum has the Coulomb interaction, and in the light part, we will introduce the spin exchange interaction. And we also apply the Mach field to induce the Zeeman splitting into the system. So, and what we calculate is the charge susceptibility of the quantum dot. And by using this, we can calculate the mesoscopic competence and the resistance. So, and I use the numerical method, which is called as numerical renormation group. It's just a numerical method which implement the idea of a renormation group, and it is known to work very well for this kind of quantum dot system. But I want to skip the detail of this method. And in this calculation, we extract this spectral weights with respect to this charging quantum dot operator. Then, by using this Riemann representation, we can calculate the charge susceptibility. Energy, so we can this in energy, this spectral weight is accessible, and we obtain the ideal energies doing that. First, we first calculate the inner part of the child subservability, and by using Cramer's correlation, we can calculate the real part. So we can get all the components of the child subservability. Okay, then we see why we have such kind of the relaxation resistance in our system. So the child subservability, the finite child subservability should have finite spectral weight for this value. And so in the absence of dot recoupling, so here the dot is singly occupied. But by connecting the dot and reservoir, then the ground state is the manual ground state is hybridized like this. So these are the states which can be obtained by allowing one electron tunneling and two electron tunneling. So with that coupling, we have the finite values for this. Then what we have is that we have some particle-hole pair in the leads. Actually, particle-hole pair is responsible for the resistance. So here we have the particle pair, and due to some relaxation process in the quantum dot, they will be together and emit some energy, so some dissipation. So this is the reason why this resistance is called a relaxation resistance. So it is based on the relaxation of the charge core pairs. So this resistance is proportional to how well the particle pair can be generated in the system. So as the number of particle pair increase, the larger the resistance is. So this is a typical graph for the charge subservability. So first look at the inner part. So inner part is just proportional to this value. So if you have larger value for it, then the inner part is increased. Actually, at higher frequencies, then you have more possibility to have particle pairs. So there are more many ways to make the particle pair. So the inner part just increase in magnitude. But eventually it decreases. It's just because we have the finite bandwidth. The finite band will limit the energy of the particle pair. So we can have the particle pair whose energy is larger than the bandwidth. So we have some decrease. But so this part is out of our concern. So just look at this part. And here, especially at very low frequencies, so here are some enlarged figures. So please see this dashed line. So at very low frequencies, the inner part is just proportional to the frequency. Then by inserting to the formula here, so the inner part is absolutely proportional to the frequency, and the real part is almost constant at zero frequency. Then we have this constant. So what we get is that here, so this red line is the resistance. So this value is 1/4. So here we have two channels, one for spin up and the other for spin down. So we have two channels, and each one contributes to the resistance 1/2. So two resistance in parallel. So the total resistance is 1/4. Small deviation is just an aspect of the energy. So it's nothing. And see the capacitance. And here, the Fermi level is aligned with the quantum dot level. So we have relevance. So it means that we have very high density state at this condition. So we have enhanced capacitance. So you should remember that the capacitance capacitance is proportional to the denser state. But here the system is Kondo regime. Kondo effect induce on some kind of artificial resonance errors at the Fermi level. So this Fermi level really can contribute to the child transport. So it acts like there is some relative level here. So it means that we have very large dense state here. Then by following the main period interpretation of the capacitance, we should have very large capacitance here, but in reality, in our calculation, we have very small capacitance. So it means that the quadratic capacitance can be, especially the quantum capacitance can be, the quantum capacitance can be related to denser state, but the state should be real state. The real state to take electron into its state. But the Kondo state is induced one. So it's not real state. It's not a real state to take charge into the level. Actually, there is no level. No real level at the Fermi level. So this shows that the quantum capacitance is not always related to the density state. So the mean period interpretation can be wrong in some cases. Now look at to the resistance in high frequency region. So this graph shows resistance as a function of frequency in the logarithmic scale. So at low frequency we have this value, this universal value. So nothing interesting. But at high frequency, we have a peak. We have two side peaks, here and here. This for the Kondo regime, and this for the single particle resonance regime. But anyway, we have similar structure, two side peaks. And the peak position is identified with the Kondo temperature, or the effective level broadening of the resonance of the system. It can be the Kondo temperature if we are in the Kondo regime. This peak is quite new in a sense that this peak does not exist if we turn off the Coulomb interaction. For non-interacting system, we have no such a peak. And actually, and now we apply the external magnetic field to induce Zeeman splitting. So at low Zeeman splitting, we have two peaks here and here. And now we increase Zeeman splitting, and suddenly we have some kind of single peak centered at the zero frequency. And the peak height is much larger. And the condition when we get this peak is that the Zeeman frequency is compared to the Kondo temperature. So in the absence of Zeeman splitting, the peak occurs at the frequency which is equal to Kondo temperature, and in the presence of Zeeman splitting, the temporal peak appears at the Zeeman splitting equal to the Kondo temperature. Okay. And for larger Zeeman splitting, all the resistance goes to the universal value, because with large Zeeman splitting, actually the state in the Kondo dot is simplified. So that we have only one single channel. So then we return to the universal value 1/2. And these two graphs show the resistance along the zero frequency. So for following this line, we have a single peak like this. So as a function of Zeeman splitting, we have a peak here. So the peak position is identified as the Kondo temperature. Then why do we have such big feature in this system. They are due to the Coulomb interaction. By turning off the Coulomb interaction, the peak disappears. So this phenomena, we can say that this phenomena is attributed to the Coulomb interaction. Then how? First, see why we have a peak, relation peak at these finite frequencies. Actually, in Kondo's state, it's the dielectron and the electron in conduction band, the reservoir, has some spin binding. So this is the origin of the Kondo effect. So there are effective anti-ferromagnetic coupling. So they form a singlet. So we have singlet binding. So if the strength of this binding energy is simply same as the Kondo temperature, then by applying energy rather than Kondo temperature, we can break it. Then particle pair like this can be generated more easily. So this is the reason why we have a peak here. So by applying the energy compared to the Kondo temperature, the spin binding is broken, and the particle pair generation can be enhanced, which lead to the enhancement of the resistance. Then, but in the presence of Zeeman splitting, we don't have to supply the energy because the Zeeman splitting can compensate for the energy. See this process. So here we have spin down, and in tunneling process, in second tunneling process, this spin can be flipped, and the pair of particle pair is generated at conduction band. Then by flipping, we have some energy gain by Zeeman splitting. This energy gain can be used to compensate, to be used to break the spin binding energy. So this is the reason why we have very pronounced resistance at zero frequency. If the Zeeman splitting is compared to the Kondo temperature. So it means there are the other processes which keep the spin in quantum dot unchanged, but there is no energy gain at all. And we found that the spectral weight for this process this process vanishes completely for zero Coulomb interaction. So I already told you that this peak feature disappears in the absence of Coulomb interaction, and this spectral weight also vanishes in absence of Coulomb interaction. They both become finite in the presence of Coulomb interaction. So we can guess that this process is responsible for the enhancement of the resistance. So it means that here we have some kind of spin fluctuation. By allowing spin fluctuation, we can increase the resistance. So by increasing the spin fluctuation, we can apply energy, or we can apply the Zeeman splitting here. So, and this spin fluctuation is assisted by the Coulomb interaction. Without Coulomb interaction, this process does not happen. It has zero spectral weight. And one thing which is interesting is that this value also vanishes in the particle symmetric point, which means that at a condition where the energy adding one electron and subtracting one electron are same, there we have particle symmetry, then this value goes zero. It's because that for this process there are two possibilities with respect to the order of the tunneling. Actually, there are two tunneling, so there are two cases. Which one is first? So after the electron is take a reservoir electron tunnel into the Kondo dot, then the electron in the Kondo dot can go out of the Kondo dot, or we have the reverse process. And due to the fermion nature of the electron, both processes have the minus sign, so it has the opposite sign. And in this point, both has the same amplitude. So in this case, they cancel out each other due to the destructive interference. So we have zero spectral wave. And in this case, the resistance has no enhancement error. So this is another proof, another evidence is that this process is really responsible for the enhancement of the resistance. So spin fluctuation enhances the resistance, especially the relaxation resistance. And now we consider two-level cases. Just adding one more level does not change the physics discussed up to now. But here we add one more interaction, the spin interaction between electrons in two orbitals. And look at the doubly occupied cases. So here there are six states are possible. So two electrons can form singlet in orbital 1 or in orbital 2. And each electron can reside in different orbital levels, one in orbital 1 and the other is in orbital 2. Then they can form singlet or triplet. So as a function of the spin exchange coupling, the levels, the order level can be changing. So the difference, the energy gap between this singlet state, the S3, and triple state is J. So here J is 0. But usually J is negative. So you can remind yourself the Huntu coupling. Usually in molecule, the fermionic coupling is more preferred due to the fermentation. So J is negative. So we consider in this region, especially here, where we have singlet triplet transition. By tuning this exchange coupling, we can derive the system to the singlet triplet transition. So the splitting between two states is can be written like this. So it is given by this formula. So by tuning J, we can derive the transition between singlet and triplet. The quantum state in near the singlet triplet transition is well studied in early 20th, early in 2000. So the low energy Hamiltonian can be written this kind of two influential Kondo model. So here we have two spin 1 and 2, which are coupled to the condensate spin, and two quantum spin are coupled through this coupling Ji. So Ji is given like this. And depending on Ji is small or large, we have two states. So in fermionic side, then the ground states are triplet, but now Kondo dot is coupled to reservoir, and reservoir spin can screen one of the two spin by using Kondo effect. So only one spin is on screen. So the ground state is spin doubled. And here we have one energy scale, which is the Kondo temperature. In the other side, we have an anti-fermionic spin coupling. So here it's like singlet is the ground state. So simply the system is in spin singlet state. And one more thing is that in the interference side and at very near transition point, we have two state Kondo effect. So still the true ground state is the spin singlet. But before we reach the ground state, the Kondo screening takes place step by step. First, one electron, for example, say S1. S1 is coupled antifermatically to conduction spin. Then we have a Kondo effect. So one electron is screened out first at the energy scale of Kondo temperature. And after that, now we have the antifermatic coupling between two spins. Then we have another kind of Kondo effect. So the second spin is coupled to the Kondo-induced resonance level. Then the second spin is also screened, but at more lower temperature, TKI. Usually TKI is much smaller than the first Kondo temperature. So after that, the ground state is spin singlet because two spins are screened out. So then this respect should be revealed in the resistance, following the resistance declaration. Still, low frequency limit is not so interesting. I mean, as a function gate and the interaction, the low frequency resistance is just 1/4 the universal value. The small deviation is due to the artifact of our numerical method. So actually, we are more concerned in here where the gate voltage is just gate charge is 2, where the ground state has only 2 electrons. But no matter what value the gate voltage is, we have the universal resistance for the low frequency regime. But in high frequency regime, we have the peak structure again. So the first figure corresponds to the ferromantic regime. So here we have the under-screen Kondo effect. So here we have Kondo effect. And we found that the peak position is equal to the Kondo temperature. And these two figures correspond to the two-stage Kondo regime. Actually, here we have two peaks again. And as J is increased, the peak position is moved from low frequency to high frequency. And actually here you see only one peak, but by amplifying this part, actually we have another peak here, which is hidden in the tail of the center, the inner peaks. So actually we have 4 peaks, 4 side peaks here. And the first one occurred at the second temperature, and the outer one happens at the first temperature. And in the anti-ferromantic region, where the ground state is a spin singlet, we have no peak structure here. And this peak position, which is shown in blue dot as function of J, is identified with the Kondo temperature, which is shown in the red circles. So we found very nice match between the peak position and Kondo temperature. Then why do we have this picture here? The logic is same as the single level cases. So actually here we have still spin binding coming from the Kondo effect. So applying the energy which corresponds to the Kondo temperature of the spin's Kondo model, we can enhance the particle pair generation. In two-stage case, this enhancement takes place in 2 steps. First, at lower Kondo temperature, and the second Kondo temperature, we have the enhancement of the resistance, and later, at higher Kondo temperature, we have another enhancement of resistance. So by breaking the spin binding, we can enhance the resistance. But in the anti-ferromantic case, the spin binding is quite strong. So it requires huge energy. So this is the reason why we have no peaks at all at low frequencies. And here again, this peak vanishes if we approach it to the particle symmetry point. In contrast to the single level case, we can provide some experimental confirmation for even in the absence of Zeeman splitting. Usually at zero temperature, the low frequency resistance is simply given by the universal resistance. But we cannot implement zero temperature. We are living in finite temperature system. Then in some cases, the temperature can be larger than the second Kondo temperature, which can be small. It can be exponentially small. So at some finite temperature, like here, the temperature, when temperature is equal to the second Kondo temperature, we can see this enhancement of resistance. So even without Zeeman splitting, we will measure the resistance enhancement by varying the spin exchange coupling like this. And in the Zeeman splitting, in the presence of Zeeman splitting, again we can get the single concentrate peak at when the Zeeman splitting is compared to the Kondo temperature. Because by applying the Zeeman splitting, we have the energy gain by the Zeeman splitting, and again without applying energy from outside, the resistance can be enhanced by making more particle pairs. In two-stage case, this enhancement happens at two steps. So when first one happens when the Zeeman splitting is equal to the second temperature, and the second enhancement happens when the Zeeman splitting is equal to the first temperature. More interesting happens in the interferometric case. Interferometric case, we had no peak at all at high frequencies, so story is quite different. But even in this case, for very large Zeeman splitting, we have enhancement of Zeeman splitting. It is due to the magnetic field induced Kondo effect. So by applying Zeeman splitting, the one of the triple state has lower energy, and eventually when the Zeeman splitting is equal to the single triplet splitting, then we have a degenerate two states, and these two states can act as like a spin up and down state. And here we have effective spin half Kondo model again. Then so here in this point where the arrows indicate, we have the exact Kondo state. At that Kondo state, we recover this double peak feature in the resistance. So when we have peak at resistance, we have peak when the frequency is equal to the Kondo temperature. And of this the degenerate point, we have effective Zeeman splitting between two spin states. Then again, we have the central peak in both cases. I mean, there's some negative Zeeman splitting and positive Zeeman splitting. But actually, before we calculate this, we expected some kind of symmetric pattern and symmetric resistance. I mean, so actually here we have peak here and here for negative Zeeman splitting and positive Zeeman splitting. But here the magnitude of the height is quite different. Actually, don't understand it clearly. There are many reasons for that. Actually, the Kondo temperature is a function of the Zeeman splitting, because the effective model, in this effective model, these parameters are, all the parameters are function of Zeeman splitting. But it alone can explain this huge difference in the resistance. Possibly other term, some more spurious term, can work and is operative for this enhancement resistance, or maybe some high-end structure are responsible. Anyway, in this picture still can be understood in terms of the particle enhancement by inducing the spin fluctuations in this system by applying Zeeman splitting or applying finite energy. Okay, let me conclude my talk. So, actually, what we found is that in the presence of Coulomb interaction or in many-body effect, we can induce some spin fluctuation into the system by applying energy or some spin interaction into the system, and then we can have the larger relaxation resistance. So it can, and this phenomena can have diverse effects according to the system we use. So in the second part, we introduced some spin exchange coupling, but still the physics is same. Okay, thank you for listening.
Is there any upper bound to the general section resistance, or it can grow forever?
I think that there is no upper bound. Actually, let me see. We have seen that the peak, the peak height increase as the Kondo temperature decrease. So it's simply because here the resistance is inversely proportional to the frequency omega. So if we have the lower Kondo temperature, then the omega is smaller, then we have the larger resistance. So there is no upper bound. If you can have the smaller Kondo temperature, then we have much larger resistance.
What would be the best way to tune relaxation resistance experimentally or?
Experimentally, one way is to apply magnetic field to control the Zeeman splitting. And if we have two-level system, we can apply some gate to tune the spin exchange coupling. Then by using this, by tuning J, we can change the Kondo temperature. Then we can modulate the resistance.
In a model where the Kondo physics is not only in the spin but also in the isospin sector, for instance in nanotubes, when you have SU4 symmetry, you would expect to have more channels, and then the quantization of the generalized resistance should be H bar over A. Yes, correct.
So actually, here actually the resistance comes from the charge response. But here, by allowing spin fluctuation, we could increase the charge resistance. Then by allowing another fluctuation, the isospin fluctuation, maybe we can have the same logic to enhance the resistance.
And in the last part of the talk, this part.
Yeah.
You have calculated the charge relaxation resistance, but the capacitance.
We didn't. Yeah, we didn't. Well, if you want, I